Hey, this is Jacob Danner with Technically Speaking at Source Allies, and today we're going to be talking about GEPA. And so I think GEPA is just the coolest. It is an optimization or search algorithm, and it's really interesting because it takes ideas from evolutionary computing, and then we leverage LLMs as kind of the engine for that evolution. And so we can kind of define a compass of how navigating the search space should work by defining a fitness function. And then we can leverage the pretty general intelligence of LLMs to mutate our candidates. And then with those two pieces, we can set up a pretty cool loop where we can leverage AI to find solutions in the search space that we probably wouldn't have gotten by hand. So it's pretty interesting stuff. And so I want to give a shout out to the people who created it. GEPA stands for Genetic Pareto. And if that means nothing to you, don't worry about it. You'll understand by the end of this talk. But it basically just defines the search space and kind of how we traverse it. So kind of to motivate why I care about it is because it essentially allows doing like machine learning on a prompt, which is such a cool idea. So for our demo today, we're going to be talking about kind of an accuracy metric. So it's quite hard to scalably define a way to evaluate LLM outputs in a deterministic way. And so I would argue that doing it deterministically is almost a mistake in most cases. And so I think it's something that can be learned. And so that's what we're going to be demonstrating today, how GEPA can learn the judgment that you have into a prompt that you can then run however many times you want and have pretty good sense that it is encoding the same judgment that you have when running your evaluations. And so to demonstrate this, I've kind of created a little toy data set here where we have 4 examples, and there are 6 answers per question ground truth pair. So I'll read this one like explicitly, and then we can see how it goes from there. But so given this prompt, what was company's monthly recurring revenue at the end of December 2024? We have a ground truth where there's a specific number involved. And so then I've kind of enumerated the cases of what I think would be right and wrong about different answers to this. So obviously an exact match is correct. If it chooses to round, like 424K is the same basically as this. Like I'm the judge here. I get to say that that is totally okay, and I have. So that's labeled correct. And then also another case would be it gets the main thing that we care about correct, but then there's additional information. And so to me, that is no problem at all, as long as the core of the question was answered correct. And then moving on to the incorrect cases, if the number is just blatantly wrong, then that is obviously incorrect. If the rounding is wrong, so 423,800 should round to 424, so rounding down is an error. And then the wrong metric. So if it reports the same number here, but up here we're talking about monthly recurring revenue, and down here it's annual, then that's also wrong. And then discussing another case, so if we expect that our application will be returning what I'm considering like a scalar value, where it's pretty much just like a factoid, as well as like a table where there's basically multiple facts, then we need to be able to encode correctness and incorrectness for those separately, because they are kind of different cases. And if you've ever worked with like a off-the-shelf answer correctness metric, you've probably felt the pain of this kind of difference between these two things. Similar thing, we have a question, we have a ground truth, and exact match, good. Rounding, They're all rounded correctly. Good. If there's an extra column, I don't care. Like, I got the main stuff that I wanted in my ground truth correct. Incorrect would be if the numbers are just wrong. Obviously, that's a problem. Another case could be that all of the row values are there, they're present, but there's a mix-up between a row as its month value and its revenue value. So I was saying this is another case of incorrect where October should actually be 394. So this is basically the numbers here are swapped. And so that kind of is a unique test of all of the values are there, but they're out of order. So that's a problem. And then another issue could be just like a wrong column name. So revenue and net revenue could sensibly can be considered the same thing, but if in my domain I treat them as different things, then of course I'm going to label this as incorrect. And so this is kind of just an example of, like, I have my domain knowledge, I can encode it by labeling things right or wrong. And then we have basically the same thing, except we have these for basically a validation set. So 2 questions train, 2 questions validation. And just like in any machine learning, you kind of want to separate out the stuff you train on from the stuff you validate on to know that your solution is pretty general and can go beyond the distribution that it saw during its learning process. Given all of that, you can imagine that it would be useful to have an LLM as a judge that basically has learned all of my domain information here via me encoding things by making like a labeled data set. And so obviously there's not a lot of data here. It's really only 6 questions times 2 that we're going to show the train. So 12 examples is not a lot, but I think that we can show that it's enough to make a meaningful impact when learning a prompt. So I pulled up a script that I wrote that pretty much runs GEPA. And so I'll give kind of a high-level overview of what's going on, but then I really want to dig into an actual run log. I ran the program. Let's look at what output, and then I think that'll help you understand what's going on with this algorithm. So overall, I'm just like setting up tracing so that we can see what my AI is saying. I'm using OpenRouter and GPT OSS 20B for the only reason of it's cheap and fast. And then for my classification, I'm treating this as like a binary classification problem where it's either fully right or fully wrong. Another aspect of you could go more nuanced here if you want. And then I'm just going to glance over some things, but just accept it for now. So a reflection language model is going to be used by GEPA for actually mutating our candidates. So we make one of those. And then just a way of getting the output from it. And then importantly, we have our load data set function. So that is just the same exact data we were just looking at. And then as I mentioned, we need to define the compass of like how to navigate the search space. And so that's our evaluator right here. For our evaluator, we basically just need to be able to run a candidate and then assess how good it is. That's the core of it. And so what we see here is that exactly. So we take in a candidate, which is going to be a prompt. So it's a string. And then we have an example, which is going to be an instance from our data set. And we are going to be returning a float and a dictionary from here. So basically, we're going to set up an LLM so that we can call it with our prompt, system prompt being the candidate string. And then it's going to output our classification. So either that 0 or 1. And then we can actually run it. And then What I care about here is accuracy. That's the crux of this mattering at all, is whether or not this prompt is able to encode how I feel about whether something was correct or not. And so this is going to be able to run our candidate and then compare it to our ground truth of what I labeled as either correct or incorrect. And so then GEPA expects you to return things in this shape where we are going to return our float of 1 or 0 here. And then this stuff is called additional side information. So basically, it's pretty interesting because in more typical machine learning, you work off of like direct gradients where you really only have a number to hill climb on. So like accuracy is an example of something like that. But with GEPA, you're able to leverage language models so you can give them more information. Rather than just a number, you can give them the actual strings of like, this is what I expected, this is what was predicted. And so you can do a lot more fancy stuff with this than what I'm doing right here for our toy example, but that's how that works. And then to actually run everything, we're going to be loading our data set. And then important things on this are, I guess I haven't mentioned yet, this Optimize Anything API is really cool. It supports a couple of different modes, but we're just going to be doing the like generalize mode where we pass a data set and a val set. And so you can see there we're giving our evaluator, our data set, and our val set. And then interestingly, so a seed candidate is nothing special other than the first instance of a candidate. And so basically that means the first round that this thing goes is going to plop into evaluator with candidate as here. So exact matches equals 1, else 0, a naive take on how to make this thing work like we want it to. But another cool instance of kind of that side information is I can pass kind of strings for background context. I can tell the reflection language model that's going to be evolving our candidate background information. So I can say like, we're trying to learn a system prompt that classifies correctness or not. We have to generalize to new data. And then we can give background. So if you have like a lot of domain knowledge or something like that, you could put that here. But I've just put something to kind of encourage like different mutations to be. I put something here to encourage our mutations to kind of be more drastic than they otherwise might be, just as a means of demoing this. And then config, we can set, this is basically your budget of how many runs you want to call. And we can set our reflection language model. And yeah, so I think that is enough overview to actually jump into some logs and see what the traces look like, I guess. So as I mentioned, that iteration 0 is kind of unique where we don't have a baseline. So we need to run our seed candidate over our validation set. So just as a reminder, our validation set is 12 examples. And so our seed candidate got this degree of accuracy as an average over those 12 examples. And so then for our next iteration, you can see that we select program 0 and it mentions the score that it got on the val set. And then the reflection language model is going to propose a new candidate. And so this is pretty interesting. You can see right away it's trying to write Python code. So obviously I'm not running this Python code. So this is just going to be kind of happening in the AI's brain space. But you can kind of see what it's trying to go for a little bit. And then, so importantly here, this is our new candidate. And then after we have a new candidate, we are going to run our new candidate against the baseline. And the baseline here is we selected program 0. And so we're going to run this over a subset of our training data. And then that's our baseline score. And for our new candidate to be better, it has to strictly get a better score. And so it looks like on the subset of training data we're looking at, the old candidate got a 4 out of 6. Many batches are 6 as we configured them. Yeah, so because our new subsample score 4 is not any better, we're just going to keep moving on. Don't even bother running it against the full validation set. It's not better against this mini batch, so it probably won't be better against the full validation set. That's the idea. So then another iteration, we're going to, again, select from our candidate pool. And so right now, program 0 is the only one in our candidate pool. We're going to propose a new candidate, kind of a similar situation here. And then same boat again. So it looks like on this subset of training data, the original prompt got a 5 accuracy out of 6 rather than 4. So this one's not any better. No need to follow up with the val set. The next iteration, we're again sampling from our candidate pool, which only has one thing, so we get program 0. And we make a new candidate. And then this one, 4 is better than old score 3. So we are actually thinking that this candidate might have some legs. And so we want to run it against full eval and see how that goes. So remember that our original candidate scored basically 66% accuracy over our val set. And coming back down here, our new program had a score of 91% on the val set. So obviously that's better. We want to keep this one around. And so all of these logs basically are that kind of Pareto piece that I briefly mentioned, but pretty much a Pareto frontier is basically just like you define the slots of your things that you care about, and then a candidate can dominate that slot. So considering that we have our 12 evaluation questions, you can think of that as 12 slots where program A might really be exceptional at the validation item 0, but it's terrible at all the others. A Pareto frontier defines a bunch of slots, and then we keep around the thing that is the best at the slot. And so in our case, we have 12 eval questions. So those become 12 slots. And so basically that means that if we have a candidate that is terrible at 11 out of 12 things, but it takes on the new high score on this 12th slot, then we can keep that around because it's dominant on that slot. And so here we can see the val set scores for our new program. So on question 0, we got 1, a lot of 1s, so it did a good job. And then it looks like on the final question, it got a 0, so got that one wrong. And so that means on our frontier, we are going to actually want to keep this thing around because it did a great job. So because our metric is like a binary 1 or 0, it leaves little room for like incremental improvements. And so it's likely that we'll see a number of ties. And so you can see here, like we updated our Pareto front. What this is saying is that for question 0, both program 0 and 1 our original and then this one both got a perfect score. And then for question 1, it looks like our new program was totally dominant. And so yeah, that's basically what's going on here is we're keeping track of, for all of the slots, which program holds the high score. We can see here that on the one that the 11th slot where our new candidate failed, it looks like the 0th program holds that slot. So that is why we can see that our best program as per aggregate score on Valset is 1, means that collectively with our different candidates we have perfected our Valset. But that also means that, but I mean, obviously we just talked about how this is a case where we're looking at it in aggregate. So for iteration 5, we begin by plucking a new starting candidate off of our Pareto frontier. And how that works is basically it's kind of like a lottery ticket or something, where each program gets as many tickets in the jar as slots it dominates on the Pareto frontier. So a better program is more likely to get selected as a starting candidate, but it is possible for anything on the frontier to get selected. So we're back to kind of what we've seen before. It's proposing a new candidate. And then this one also had a better score, 5 rather than 4. And so that is in comparison to our starting program. And so we're going to go to the full eval set. And as you can see, looks like we got a 1.0 entirely on the Valset, so that's great. 12 out of 12. Yeah, so that pretty much shows the different cases of what may come from a GEPA run. And so I guess it's kind of obvious that at the end, once we have these number of different candidates, we're going to select the one that is the best overall. And so there's this thing that you can do to visualize your GEPA candidate tree. And so obviously there were more iterations than show up here because we only show things here that were good enough to keep around at the point in time. So our starting candidate with that seed candidate did pretty good, but there were a number of questions where it got zeros on our val thing. And then over here, almost perfect, just one failure, a much wordier prompt. And then this one, similar prompt, but we are perfect. So that is great. That shows that we can use GEPA to encode our domain knowledge in a way to judge what correct or incorrect is. But the really cool thing about GEPA is that you can go way beyond this. You could, this library I'm using is called the GEPA Optimize Anything API. And so the core idea driving that is right now we are obviously optimizing for a prompt, but there's nothing inherently special about a prompt. As long as we have a string and then some way that we could measure how good the string is, we can optimize anything. So let's briefly look at the actual traces of what happened during our training run, because we kind of saw the results of it, but you didn't get to see the inner workings of like what that reflection language model was actually given and how it did what it did. So we can see here like an example of given our original system prompt and then one of our examples, the output. So we're going to get a number of those per iteration, obviously, and then I named them so they're easy to see. We can see the reflection model is going to actually get to, let's read through this. So it's got a prompt, you're an optimization assistant. This is our objective that we put in there, and then also our background. So those things get plopped right into this prompt for the reflection language model to do stuff with. And yeah, so then we can see the current thing, the current state of the world that we're trying to optimize, which is our seed candidate. And then we get to see evaluation results. So this is the stuff from that dictionary that we were returning from our evaluator. So for example 1, we expected 1, predicted 0, and our score was 0. So looking at this now, I am realizing that I definitely should have included the actual example in our evaluator to return. So if I were to fix this, I would do like example, and then I could get like example, and then we could. So if I were to fix this, what I would do would be to, I was actually returning the expected and predicted when I should have been returning the actual strings there. So I would have done, we have our example, I could get like the ground truth off of there, and then here I could rip off the actual answer. Oops. I could get the actual answer, and then that way this thing would actually see the real strings that came in, which would obviously be far more valuable. So I'm impressed that it was able to optimize anything, given I gave it so little. Like, that is not a lot to work with. So sorry, AI. You see, this is our mini batch. So I mentioned it's size of 6, so we see the results for 6 things at once. And then there's this task of like, actually do the optimization, suggest a new thing. And so then this is the next suggested candidate. And so, that is what things actually look like when you are looking at the traces. So I think it's pretty awesome to be able to see this and kind of imagine of like the different things you could surface here. Like you could encode a lot of domain information. You could use like another LLM as a judge to kind of add suggestions here of like what went wrong, or you could do whatever you want. Core idea being it's useful to pass context so that when we are actually trying to create a better candidate, it has rich, meaningful stuff to build on top of. And that's kind of the thesis of GEPA. It's less sample efficient than if you had just a single number that you were hill climbing on. So it's pretty awesome. And I also made these kind of quick slides to run through just as tie everything together. I think things will make a lot of sense here now that you've kind of seen everything. So we can imagine we have a training data set and a validation set. And then we have our seed candidate. So we're going to call that C0, run that over our full val set, and then that's our baseline. And so at this point, the Pareto frontier is fully dominated by our seed candidate. And then for round 1, we are going to pull a mini batch from our training set. We're going to sample our candidate pool. So grab something from here. There's only one. We grab that. And then we are going to run the baseline. So take our selected thing against our training mini batch, and then we get the score, where the score is the sum of its scores. And then we're going to do the LLM mutation, where we create our new candidate by reflecting on the output of this, basically, the baseline scores and traces. And then given that, we're going to run our new candidate over the same data, and then we compare. Is the new one better than the old one? If so, then we're going to move on to the full file set eval. So we have our old frontier. We run our new candidate over the val set. And you can see here for the V1 example, our new program is better at that specific problem and nothing else, which means that it's now going to get put in here as the dominant one for that problem. And we add it to our candidate pool. And then another case would be in the following round where we, again, same thing. Now we have 2 candidates in our pool. We're going to randomly grab one. It happens to be C1. Do our baseline, do our mutation, do our mini batch score of our new program. This one is worse than our old one, so we are actually just going to discard our C2. No sense in running the full val set against it because we already know it's not good. And so then our Pareto frontier doesn't change at all. And then the other possible case that could happen in the following round would be same boat as before. Our new candidate is better than the previous candidate, so we move on to full val set. But here, our new candidate does nothing special on the val set. So we do not put it on the Pareto frontier, and we do not add it to the candidate pool. The real power of this thing is that it's a loop, and so we can do it however many times we want, and we can generate more candidates and hope that they're going to be better. And so eventually, hopefully we reach a point where we have candidates that are performing very strong against our validation set, and then we are going to actually pick the best one. And so we could deploy that. I hope I conveyed why this is an interesting approach, and there's a lot more to it that I didn't have time to go into today, but I tried to demonstrate like a practical use case and then also try and show that it's not magic. So I hope you understood the algorithm and why you would want to do it. And there's a lot more if you care to learn more, so dive in. And yeah, this has been Jacob Danner with Technically Speaking at Source Allies. If you have a topic you want to see covered, please comment it down below and check out our website at sourceallies.com to learn more about us. And thanks for watching, and we'll see you next time.